Yes, and I'm live and I'm back. It's insane. I have not stepped in this building since Tuesday. That is a long time for me. I don't know. I can't tell you the last time I took multiple days off in a row. Multiple days off, literally, it's probably when my daughter was born. Oh, you can hear me through that other speaker. Let's turn me off over here. There we go. Now you're off. There we go. Good. I usually don't take that many days off, as you probably can tell by this entire school year. I don't like taking days off, but I got that second vaccination on Wednesday of last week, and it wrecked me. It hits people differently. You know, I've heard stories of an older acquaintance of mine who is in her like 80s. She got the second vaccination and she actually got dehydrated and fell at her house. Actually, no, I think that's why she got dehydrated. She fell at her house and then now this is a real story, nobody found her for 18 hours. And she was like on the ground. And that's how she got dehydrated until eventually like her son, who comes by regularly once every couple of days, found her. And she's fine, you know, otherwise why would I be sharing this terrible story with you? She's fine, but it's like one of those things, like it has different effects on different people. For me, it was like a full body, like, oh my gosh, everything aches, even my even my fingernails. It was insane. Anyway, but we're back. I only missed one day for you guys, right? Sweet. That's actually pretty decent. 8 days is kind of screwed, but we'll figure that out as we go along. Anyway, before I forget, anyone in the chat right now, please make sure you leave a comment right there so I can see it right there. That'd be fantastic. I will check that in a little bit. Just a reminder, last week you had to get done some free response questions for me. And I left this as a little bit of a challenge for you. I emphasized that idea of like, hey, challenge yourself, push yourself. I gave you 4 free response questions, and I was hopefully very clear that I said, hey, get done 3 of them. Get done 3 of them. If you want to get done all 4, get done all 4. But if you can get done 3 of them, get done 3 of them, and that would be absolutely fantastic. My goal for today, I want to go over maybe not all of them, but at least a few of them, at least 2, let's say, of the free response questions I would like to go over with you in good detail. What I am going to be providing for you is I am going to be giving you a copy of the scoring guidelines electronically. I'm going to do that sometime later today, but I'm going to give you a copy of the scoring guidelines for those questions so you can kind of see how you did compared to what College Board grades it at or something along those lines. It's going to be great. What is today, the 22nd? Sweet. We have about 2 months. 2 months until your AP test. 2 months. Oh, it's going to be great. Do you guys know what Carvana is? You do? I had not heard of it until Tuesday or Wednesday of last week. Like, literally, bought a car, got it Friday. What? No one else knows what Carvana is? All right, cool. It's like, now, please correct me if I'm wrong. It's like basically like vending machine cars. Oh, yeah. You know? It's pretty sweet. Look. So on Thursday, my wife and I have been looking to get a new car, did all of our research. The mechanic is like, hey, try this out. And we're like, okay. So we go on the website. We're like very skeptical of it, very, very skeptical of it. And then ultimately on Thursday, we're just like, this looks good. And like, we're reading all the fine print. We're like, we have 7 days to return it. Let's just do it. Okay, let's do it. So we bought the car, and then they were just like, we'll deliver it on Friday. I'm like, what? Dude shows up Friday night. He's like, here you go. You've got to be kidding me. This is insane. So now we have 7 days. Oh, 7 days from last Friday. I'm going to bring the car to the mechanic like tomorrow. He's going to do a once-over on it, and he's going to be like, yay or nay. My kids have already fallen in love with it. It's a mid-size SUV with like seats in the back that can fold down. So I'm just saying. Anyway, I just wanted to say that because it was funny. Carvana. Who the heck would have known? Okay. So what I'm going to suggest that you do. Number 1, I would like to go over at least a couple of those free response questions. Again, not all of them, because I am providing for you the scoring guidelines. Couldn't think of the phrase. I will give you the full heads up. My intention was to knock out a major because last Tuesday, we did some review in class last Tuesday. And then Thursday, I gave you those free response questions because I knew I was going to be out. My intention was to give a major, but Friday, I was not coherent enough to do much. Just again, this vaccine just kind of punched me in the side of the face. So what I am going to do is I am going to be assigning a major assessment probably today or tomorrow, depending on when I can actually get to that, because I got a lot of stuff to catch up on. And it will most likely be due on Friday. Just giving you the full heads up. It will most likely be due on Friday. I'm going to give it to you no later than tomorrow. Absolutely no later than tomorrow. But I'm going to try and give it today. But it will be due Friday, regardless of which day I give it. It will be on Unit 5, the stuff that we've been covering, the beginnings of hypothesis testing, sampling distribution, confidence intervals, things of that nature. And then we'll all high-five each other from a distance. I hope. I don't know. You all heard about April, right? Like what's going on in April? We're going back to, yeah. It's going to be weird, right? Yeah. I don't know. I've seen the proposed schedule. It looks ridiculous. But that's neither here nor there. Anyway. Then, after whatever time we have left, I would like to take a small step into the next unit. I say a small step because we're not doing much different. It's still hypothesis testing. It's just different types of hypothesis testing dependent upon the situation that is presented to us. But we'll get there when we get there. In the meantime, what I'm going to suggest to you while I'm going over at least a couple of these free response questions, if you want to jot down some information for yourself that may or may not be helpful, or compare it against some of the responses that you did last Thursday for me, I would strongly suggest that you have that paperwork out or have those notebooks out and open. Yeah. High five me. Bring this thing across. What is this, a reading list? Get that out of here. I can't unsure. Okay, let's bring this over. Boom and boom. Why can't I make that? How do you get rid of that left part? Hold on. I gotta get rid of that left part. Oh, there it goes. Sweet. Okay. Boom. And this is, I already forgot what this was. 2009, number 2. There we go. 2009, number 2. Again, if you are on the live stream, these PDFs, these 4 PDFs are available through the most recent assignment on Google Classroom. This is what you did for me last Thursday. So if you have trouble seeing it on the computer, you could always go to the Google Classroom to be able to see this stuff. Okay. Going through this question. A tire manufacturer designed a new tread pattern for its all-weather tires. Repeated tests were conducted on cars of approximately the same weight, traveling at 60 miles an hour. The tests show that the new tread pattern enables cars to stop completely in an average distance. And again, this is what I tend to do. While I'm reading things, I try to kind of conceptualize what am I going to write down for this kind of statement. The test showed that the new tread patterns enabled the car to stop completely in an average distance of 125 feet with a standard deviation of 6.5 feet, and that the stopping distances are approximately normally distributed. Okay, that last sentence gave out a lot of information. Can I write down about this? First of all, the tests show a new tread pattern enables the car to stop completely in an average distance of 125 feet, standard deviation of 6.5. I don't see anything about a sample, the way that they're wording the question. Okay, I'm going to say that mu is equal to 125 and sigma is equal to 6.5. And I'm saying mu and sigma because they sound like population parameters that they are giving me. And if they're giving me those population parameters, then I have sigma. Okay, I'll see what I can do with this then. And they told me it was normally distributed. Yes. They're telling me it's normal. I don't have to show that it's normal. I don't have to go through any assumptions and conditions to show normality. I can use normal CDF all day long or whatever for this thing. Oh, snap. What is the 70th percentile of the distribution of stopping distances? 70th percentile. I'm going to need to jump to my calculator here. Actually, no, I'll use the one on the computer. What am I talking about? 70th percentile. What do you got to use for 70th percentile? I mean, clearly I'm jumping to my calculator over here, but hold on, let me move this over. There we go. I'm doing 70th percentile, but I'm jumping on my computer. Where do I have to go on the calculator in order to find a 70th percentile? Oh, that's stuff from algebra. Ooh. If you go normal CDF, now again, this is not the information we need right here. But if you go normal CDF, it gives you the percent of data between a lower and upper limit. So, I don't know, I'm just going to make this up. Let's say I went negative 10,000 to, well, it's 125 feet, so let me go like 140 feet with a mu of 125 and a sigma of 6.5. Again, this is not what I'm supposed to do for this problem. I just wanted to see what happens if I actually did this thing. Normal CDF, lower upper limit, mu and sigma. Oh, I got 98.9% of the data. Now, since I'm going small number up to 140, that must mean that 140 is like my 98.9th percentile. Oh, goodness, I guess I could do it again. Instead of a 140, let's try it with a 130. 130 is my 77.9th percentile. What am I finding? 70th? Sweet. I could be here all day long. I mean, I could. Let's go 126. Oh, too much. What am I supposed to do? Guess? No. Normal CDF will give you the percent of data after it's calculated. But inverse norm, you have to remember, inverse norm will give you the percentile with this proper information right here. Type in that information, boom, that data point at the bottom of the calculation, that is the 70th percentile. The 70th percentile is at approximately 128.41 feet. I'm assuming it's feet. I got to go back and double check. I think it's feet. I was leaving it up there so people have an opportunity to see that calculation and how it was exactly done. But again, just as a reminder, as you're going through these problems, identify mu, as I did on the side right there, identify sigma, and if you're going to use an inverse norm, you literally can just write down that calculation, inverse norm parentheses, and then the numbers that are on the inside. And then boom, it spits out 128.41. In fact, I'm just going to show you something real quick here. I think it's over here. Scoring guidelines. This is 2008, number 2. Get rid of that. There we go. I'll zoom in a little bit, but this is weird. This is one of the scoring guidelines that I'm going to give you. But you can see part A right there. Let X denote the stopping distance of a car with a neutral, blah, 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 blah. And then eventually they get to 128.4 feet. They do it in a weird way. They've actually figured out the z-score, but you don't have to do it that way. You could literally just write down what I just showed you right here, and that is sufficient evidence for the 70th percentile. All right, part B. What is the probability that at least 2 cars out of 5 randomly selected cars in a study will stop in a distance that is greater than the distance calculated in part A? I'm going to have to compare that with what's being asked in part C, because I need to distinguish something for you. I need you to see some clear distinction between B and C right here. B, what is the probability that at least 2 out of the 5 randomly selected cars in the study will stop in a distance that is greater than the distance calculated in part A? So 2, at least 2 or more, 2 or 3 or 4 or 5. But then, what is the probability that a randomly selected sample of 5 cars in the study will have a mean stopping distance of at least 130 feet? Here's what you have to recognize, and this is kind of how it relates to the rest of the school year. Or I'm sorry, the previous school year that we've been doing with this stuff, everything since September. Part B is dealing with a binomial distribution. Let me repeat that. Part B is describing a binomial distribution. In fact, at least 2, it looks like a binomial CDF is what I'm going to have to use. This is a finite number of trials, or a certain number of successes within a finite number of trials. That's what that problem is really asking for. Whereas part C is talking about a sample of 5 cars. Part C is talking about a sampling distribution. It's all about the way that they word these questions. In part B, they just said, oh, we're going to be randomly selecting 5 cars. What's the probability that we have at least 2 or more having the stopping distance greater than that calculated in part A? Yeah. But then part C is talking about a sample, a randomly selected sample. It sounds very similar, but the distinguishing distinguishing features are important. Let me see here real quick. What was this? It was 128.4. Okay. So let me go second bars. This is going to bring you back. Binomial CDF. I find that under the same location that I find normal CDF. 5 trials. Oh, they want a probability of success or some junk like that? Goodness gracious. I got to figure out a probability of success for this thing? Interesting. Let me flip back over here. Yeah. This thing is all weird, but let me read this statement to you right here. See if I can zoom in on this. I want people in the chat to see this. Hold on. Come on. Boom. Zoom. There we go. Again, I have no idea whether or not the chat can actually read that properly. I'm trying to see the screen that they're looking at, but it's a little bit hazy. Come on, thing, turn. Okay. It says from part A, it was found that a stopping distance of 128.4 feet has a cumulative probability of 0.7. Thus, because it's at the 70th percentile. Thus, the probability of a stopping distance greater than 128.4 is 30%. That's what they're really trying to indicate with the answer to from part A. In fact, I could draw this to kind of visualize this thing out. There's the mean right there. I don't know where the 70th percentile is. Let's just say it's like right there. That's 128.4 feet. That's the stopping distance that was found in part A. It's the 70th percentile. But now part B is talking about a stopping distance greater than that, meaning there is a 30% chance of that happening. That's the visual behind the probability of success in this particular problem. There we go. 0.3. The other thing I'll point out for binomial CDF, something that I have to remind you of, something that you need to remember, is that binomial CDF will only calculate the probability of getting that X value or less. It'll only count the probability of getting that X value or less. Meaning you could have 0, 1, 2, 3, 4, or 5 successes out of those 5 trials. But it's like, okay, well, if I select 3, it's going to go 3 or less. If I select 1, it's going to go 1 or less. But what does this problem want? Do you remember? Or 2 or more. They want 2 or more. Binomial CDF will do or less. So if they want 2 or more, we are going to have to first calculate 1 or less. If they want 2 or more, we have to calculate 1 or less, and then do a little magic here. Boom. 1 minus that answer. That 0.528 number, that represents getting 1 or less successes. And then by taking the complement, that 0.47 now represents getting 2 or more. That's what that calculation really wanted to show you in this thing right here. And you can see that right here. They did it in a weird way. In the scoring guidelines, they didn't actually use the binomial CDF thing that we used, but their calculations, again, this is the ideal solution. If you literally write down, well, it's a binomial with a binomial CDF, here are the numbers that I put in, and show all the calculations, you're fine. You end up at the exact same answer with sufficient work. And that's all that they really want. The correct answer with sufficient work and evidence to back it up. That thing. Flipping back. Let's look at part C. Now this is where the sampling distribution comes into play for part C. What is the probability that a randomly selected sample of 5 cars in the study will have a mean stopping distance of at least 130 feet? At least meaning 130 feet, 130 feet or more. Those sound like my lower and upper limits. 130 feet or more, at least 130, be 130 comma, big number. But since this is a sampling distribution for part C, squeaky noises, my mean for the sampling distribution is still going to be 125 feet. That's not going to change, but my standard deviation will. My standard deviation will. And if I'm doing standard deviation of the sample, then this would be 6.5 over the square root of 5. According to that chapter of sampling distributions, you were to take the given sigma and divide it by the square root of n, the square root of the sample size. And if you're going to be doing a normal CDF for part C, which you should, lower upper limit should be 130 comma big number. But then your mean and your standard deviation should be those numbers as I've outlined. Let's see. Normal CDF, 130, comma, big number. 125 is the given average. 6.5 divided by the square root of 5. Chappelle, 0.043 or 0.0427, whichever one you want to put there. As long as you identify what you typed in, as long as you show what you typed in, and I did, what I wrote in red is sufficient as well to kind of show that mean and standard deviation. It goes a long way for showing that evidence and understanding how the problem works. There we go, scoring guidelines. Again, a little bit weird to see right here for part C, but they did show this calculation right here, 6.5 over the square root of 5. They didn't use normal CDF, but I would suggest that you use normal CDF. Show them how you did the problem. Do not give them any leverage for taking points away from you. I have said this since September. How do the AP graders feel about you? They do not like you. They will find every excuse to take points away from you. They will. Do not give them that opportunity. Do not give them that opportunity. They will take away points every step of the way. Justify what you're doing. You can justify what you're doing by writing what I wrote in red and by writing that normal CDF as well. It shows everything that you need along with the proper answer. You don't have to go through what they're showing right here as the quote-unquote ideal solution. But it gives what you need. Oh, they hate you. They wear top hats and monocles and then take points off from you. It's insane. I want to be one of them. Have you know I've applied to be an AP grader? So far, they're like, no, you're not mean enough. Fine. Jerks. Anyway, back to this. Yeah, we'll do one more. Let me see. That was, okay, yeah, 2000. Let me see which one I want to do, though. Yeah, let's do this one. Okay. I'll do the two. Yeah, I'll do this one. I'm going to get rid of that and that. And that and that. And then we'll do this one. This is the 2009 number 5. Just zooming in here. Here we go. Come on, you. Why? I hate technology. Okay, good. It should be working now. Boom. For many years, the medically accepted practice of giving aid to a person experiencing a heart attack was to have the person who placed the emergency call administrator chest compression. Wait, what? Is that worded the way I think it is? The medically accepted practice of giving aid to a person experiencing a heart attack. Oh, there we go. Was to have the person who placed the emergency call administer chest compressions. Got it. Okay. That makes more sense now. When about 14 years ago, my dad had a heart attack on a Sunday morning. He didn't go to the hospital until Monday night. He's still alive. Just so you know. Otherwise, why would I be telling you the story? I'm just saying he had a heart attack. And he's like, I'll walk it off. All right, dude. Plus standard mouth-to-mouth resuscitation MMR to the heart attack patient until the emergency response team arrived. Cool. However, some researchers believe that chest compressions alone would be a more effective approach. Anybody take CPR classes? Nobody? Oh, gosh. I worked at a summer camp, dude. I was like certified every year for 12 years. They changed the standards every year. It's insane. It really is insane. Anyway. In the 1990s, a study was conducted in Seattle in which 518 cases were randomly assigned to treatments, 278 to chest compressions plus MMR, and 240 to chest compressions alone. Okay, yeah, they don't have to be even. A total of 64 patients survived the heart attack, That's in total. 29 in the group receiving CC plus MMR, and 35 in the group receiving CC alone. A test if significance was conducted on the following hypotheses. Ooh, they even give it to you. The null is the survival rates for the two treatments are equal. Now, yes, that is a sufficient way of stating that null hypothesis. If it were me stating this null hypothesis, I might do something like, I don't know. All right, so yeah, with MMR is equal to with just chest compressions or something. I don't know. Maybe I do something like that. The notation isn't really important, but maybe I'd do something like that. Or maybe I'd subtract them and set it equal to 0 or something like that. But they actually wrote it out in a statement. And that's actually pretty sufficient. But again, null hypothesis. Nothing's going on. No difference between the two. Innocent until proven guilty. The new method is no better than the old method. That's the null hypothesis. The alternate hypothesis, the treatment that uses chest compressions alone, produces a higher survival rate. Okay. Then we get a p-value of 0.0761. Interpret what this p-value measures in the context of the study. I'm going to show you the scoring guidelines in a moment. But again, the definition of a p-value in context. That really did not emphasize it. You know when you write something a lot, it gets like darker? I think a pen. It didn't do what I wanted it to do. So whatever. Context. Context. There is, 7.6? Yeah. There is a 7.6% chance of seeing these sampled results. I guess you can give some context to that. Sample results of treatments from heart attacks or something like that. No, it's not from heart attacks. Having a heart attack and then going through the treatment, which I have to talk about that in a minute. That's really interesting. Well, I'll talk about that in a minute. But there's about a 7.6% chance of seeing such sampled results of heart attack treatments, given that there is no difference between the two treatments of chest compressions plus MMR and just chest compressions. I want you to think about this study, though. Think about this study. Think about the reality of the study for a moment. If this is true, if this is not a made-up story, that means that when someone got to the hospital having suffered a heart attack, they randomly assigned them to one of the two groups and then judged whether or not it was effective in saving their life. Think about that for a second. Isn't that kind of rolling the dice? Like, holy crap. No, give my dad the treatment that actually will work. Like, okay, but yeah, well, we have to figure out which one works first. It's like, so he's a guinea pig? Okay. Ooh. I don't know. But yeah, I just wanted to point that out. Let me see what the scoring guideline actually says here. Boom. Oh, this isn't the scoring guideline. Still not the scoring guideline. Let's see. Come on, scoring guideline. There you are. There it is. The p-value of 0.0761. Come on. Measures the chance of observing a difference between the two sample proportions as large or larger than the one observed. Oh, yes. The direction. I'll talk about that in a moment. I'm going to go back to the question. I'm going to talk about the direction. If the survival rates for the two treatments are, in fact, the same. There it is. The alternate hypothesis is trying to determine whether or not just chest compressions alone produced a higher survival rate. The direction does matter. The direction does matter. Seeing the observed difference, the sample results, or greater. I mean, obviously, we didn't calculate what the difference was in proportions. I mean, we could do that if we wanted to. We could take 29 divided by 278 and 35 divided by 240 and find the difference between the two. And it's the p-value would be the probability of seeing that difference or more, seeing those sample results or greater in terms of a difference, given that there is no difference between the two treatments. Goodness. Then it says, based on the p-value and study design, what conclusion should be drawn in the context of study? And in this one, they actually do tell you to use alpha at 0.05. They actually do tell you to use alpha at 0.05, which is nice. If they didn't tell you that, you would have assumed that anyway. So, I don't know, it just kind of seems monotonous at this point. Let me kind of speed this up a little bit because I have to, I do want to get to that other thing. It's here. There it is. Because the p-value is greater than 0.05, the null hypothesis should not be rejected. Yes, you should have failed to reject. That is, there is not sufficient evidence to conclude that chest compressions alone produced a higher survival rate than the standard treatment. Yeah, that's a very basic answer based on a fail to reject. Now, what's interesting here, again, I keep flipping to the wrong thing. There we go. What's interesting here is that, yes, you would have failed to reject at the 0.05 level. But if they had told you that the alpha level was 0.1, you would have rejected. If the alpha level was 0.1, you would have rejected and had a conclusion that there was evidence to suggest that chest compressions alone produced a higher survival rate. But that's neither here nor there. That's not needed for Part B. Part C. Based on your conclusion, which type of error could have been made, and what is one potential consequence of this error? So we failed to reject. We failed to reject. Meaning, what did we do with the parachute? What did we do with the parachute? Did we jump out of the plane? I see several people kind of hesitantly nodding yes. Yeah, if you fail to reject that parachute, you're jumping out of that plane. You're saying, I see nothing wrong with this parachute. You're failing to reject. Which means you could die. Which means that you could have made a type 2 error. That's how I typically distinguish them. Am I rejecting the parachute or am I failing to reject the parachute? If I reject the parachute, I'm still alive, but I could have made a type 1 error. If I fail to reject, as we did in Part B, if we fail to reject the parachute, then we could be making a type 2 error and we, well, could be dead. But then they want to know what is one potential consequence of this error. One potential consequence of this error, let me just flip it over here real quick. Because the null hypothesis was not rejected, failed to reject, a type 2 error could have happened. A possible consequence is that the old treatment would continue as the accepted practice when in fact chest compressions alone would have resulted in a higher survival rate. If it was a type 1 error, then, well, you switched to a new method even though it doesn't save more lives. It saves about the same lives, maybe? I don't know. If you made a type 1 error. So you made a mistake, but about the same number of people are surviving. But in a type 2 error for this context, you could have been saving more lives. But because of failing to reject, oh well. Sadness. Okay. Like I said, I'm going to give you the rest of the scoring guidelines. I'm going to post those at some point so you can kind of compare what you did against them. Again, it was a bit more of a challenge. I want you to get used to that timing thing. Okay. I want to talk about the next unit. I want to talk about the next unit and what we are going to be faced with. I do have a short bit of notes to give you today, but first I want to tell you the story behind this guy. I'm going to give you the shortened, kind of the shortened version. I gave you a little bit of it the other week, but I want to tell you it again in a bit more detail. So there was this guy working for the Guinness Brewing Company back in the 1800s. And his job was basically, in a nutshell, quality control. He needed to make sure that this ginormous vat of Guinness beer was up to par. It tasted right. It had the proper amount of whatever it is that goes into alcoholic beverages. I don't know. I base my information on that from commercials. But in order to do that back in the 1800s, yes, I mean, yeah, he could do scientific studies of this thing, but conducting an actual like scientific study, like pulling out like a little thing of a sample from the vat, putting it in a test tube, conducting the thing, and then waiting like however many hours for the results to actually emerge. I mean, that takes time. And this guy was a master brewer. So what he did, his job, was to taste test the beer and then determine whether or not it was good to go, there's nothing wrong with it, or there might be something wrong with it. And if there was something wrong with it, in his opinion, if there was something wrong with it, then it would go for further testing in order to determine, well, what was wrong? What did we do wrong? What could be done better in the future? This is the 1800s, but it's very scientific. The problem that he was running into was that when he rejected a vat of beer and it went for further testing, they did the scientific studies on it and they found out, no, there's actually, like, there was nothing wrong with this one, or there was a mistake made. Like, I'm making these like mistakes here. What's going on? Turns out it wasn't his mistake. It was actually the mistake on the scientist's part, because the scientists were actually conducting hypothesis testing. And with their hypothesis testing, they were using a normal distribution. That's what these scientists were doing. And this master brewer was like, well, something is going on here. Why are they telling me that these vats of beer, there's nothing wrong with them, when I clearly know, based on tasting them, that they're wrong? And this guy decided to investigate a little bit and went a little bit deeper into the mathematics behind it and learned what these scientists were doing exactly in order to scientifically test the beer. And he determined that there has to be some kind of mistake. Now, this master brewer, based on I don't want to call it a scholarship, but based on the Guinness Brewing Company paying him to do this, went back to college or university and basically earned a bachelor's and a master's and a doctorate in statistics. And he figured out what was going on. And what was going on was that when these scientists were conducting their hypothesis testing based on a normal distribution, he realized that, well, your sample sizes are not large enough. And they're like, well, we can't really have a large enough sample size. Well, what do you mean? It's like, well, a sample size would be, taking a drink from all of these vats of beer. And if we were to take too many, it would really impair the results. It would impair the scientists because it's alcohol. You can be drinking on the job. This brewmaster, who now had a doctorate in statistics, eventually developed this idea of a hypothesis test that does not use the normal distribution. Now, I want to be very clear about something. There is only one normal curve. There's one normal curve, one particular shape to it, and then we fit the numbers to it. But what this guy came to the conclusion is, technically, there are an infinite number of bell-shaped curves. Only one of them is perfectly normal, but there are technically an infinite number of bell-shaped curves. And it's based on the sample size. So now, if I go to my calculator here, just to show you this, boom. You do have this normal CDF. And when you see this normal CDF, you put in all of your information, lower, upper, mu, sigma. But it doesn't ask you for the sample size. It doesn't specifically ask you. Yes, you would do that for a sampling distribution here, but none of the inputs ask you for a sample size. But if I go to T CDF, this is called they actually call it a student T distribution. The reason why he wanted to name it after himself, I guess, but he wasn't allowed to because the Guinness Brewing Company wouldn't allow him to because they paid for him to go back. Anyway, if you go back over here, they give you a lower and an upper. Mr. Markey, they still don't give you a sample size. I know, but they do give you this. This is the most patriotic statistical feature that you will ever see. It is the most patriotic statistical feature that you will ever see. Now, how do you actually calculate that? I'll tell you what it's called in a minute. How do you actually calculate that? Well, sample size -1. They actually technically do ask you for the sample size. They just want to know what sample size -1 is. I'll get that into our notes in a little bit. DF. Do you know what the most patriotic statistical thing is in the history of the world? Do you know what it's called? You could say it with pride in your voice. Degrees of freedom. America. But that's what it is. He determined that there were an infinite number of these T-shaped curves, all based on degrees of freedom. And the degrees of freedom were based on the sample size -1. There's a reason for that. It has to do with calculating various standard deviations, but I'm not going to get into the details. The general idea being that the larger the sample size, the closer that T distribution came to being normal, as everything typically is. It's just that if you had a small sample size, like, oh, I can only sample 5 of these vats of beer, otherwise I'm going to pass out. Well, I can't. Sample size of 5, that's not large enough. I know, it's not large enough. Degrees of freedom, T distribution. That would give us more accurate results. And as a result of instituting this new system, when he rejected a vat of beer and the scientist implemented his methods, they were much more accurate and they were actually able to show, yes, you should have rejected this vat of beer, and here are the reasons that we found. Oh, Guinness. They're still around, right? No one's really nodding yes. I'm really proud of all of you for not knowing about beer companies. So, okay. What a weird day. Okay, so what I'm going to ask you to do with the time that we have left, like I said, this is a short bit of it, but I'm going to give you some notes. So if you do not already have them out, I'm going to need those notebooks out and open. Haha. Oh. Hee. Ta-ta. Zoom out. There we go. And there we go. Okay. Today is the 22nd. Get over here, you. And this is going to be chapter 22. Sample means and t-testing. I don't know why. Whenever I write a singular t, I mean, I do know why. When I write a singular t, I put that little cute curve at the bottom, simply because I don't like having to guess whether it's a plus sign. Whereas in the word testing, I'll actually write the regular t. Now, I have already drawn this chart before, but I want you to draw it again. I want you to draw it again. It's a shortened version. It's a shortened version. I'm going to abbreviate a bunch of stuff. Ms. Reggie, we have a statistical test here. Which test are we supposed to use? Well, do you have categorical data? Oh, yes, Mr. Markey, we actually do have categorical data. Oh, great. If you have categorical data, that must mean that you can calculate a proportion. And if that is the case, then you have a population P, or maybe you don't have a population P. Maybe you're trying to find the population P, in which case you would use a z-test. Oh, thank you. Thank you, Mr. Murray. It's all of those, one prop z intervals and two prop z tests and things of that nature. If you have categorical data, then that's the direction that you should be going. Oh, but no, Mr. Murray, for my problem, I have quantitative data. You do? Oh, man. If you have quantitative data, that must mean that you have means. And if you have means, meaning it makes sense to take an average or something along those lines, then you can use mu. That is your population parameter for an average. And if that is the case, well, I still don't know exactly which test you should use, because I have one additional question. Do you have sigma, or do you not have sigma? Do you have sigma, or do you not have sigma? If you have sigma, if you have the population parameter standard deviation, then you should still be doing a z-test. You should still be doing a z-test. Absolutely, yes. Oh, what's that? You don't have the population parameter sigma? You don't know what the population standard deviation is for the level of whatever it goes into Guinness beer? Oh, okay. If you don't, then you're going to have to do a t-test. This is a huge distinguishing factor here. Determining which test you are to use. It's very important. If you have categorical data, boom, z-test, move on. But if you have quantitative data, you need to read into the problem and determine whether or not you have the population parameter standard deviation. If you have it, z-test. If you don't, t-test. So, for example, if you have, example here, if you have sigma, you can use the z interval x bar plus or minus z star times sigma over the square root of n. If you don't have sigma, now mind you, again, it's very similar to what we've done with other confidence intervals. Let me zoom in on this little statement right here. If you have sigma, then yeah, use the z interval, where quantitative data, x bar plus or minus z star times sigma over the square root of n. That's attempting to capture the population mean given the sample that we have here. It's very unlikely that you will have sigma in real life. It is very unlikely that you will have sigma in real life. Some problems, they'll just flat out tell you what sigma is. But it's very unlikely that a real life problem you'll actually have sigma. So if you don't have sigma, just as a little bit of a preview here, check this out. Then x bar plus or minus t star. Yes, that is a t star with a little subscript times the following. Now, normally what goes on top of that fraction is your sigma. What normally goes on top of that fraction is the population standard deviation. But on top of this one, since you don't have sigma, I'll move it up in a moment, but since you don't have sigma, you don't have it. You have to use S. What the heck is S? What is S? What the heck is S? I think it's a standard deviation, but which standard deviation? Oh. Where did it come from? This comes down to our notations. This comes down to whether or not you have population parameter stuff, such as mu and sigma, or you have sample statistic stuff like x bar and S. If you have the population parameter junk, this is the notation that you would be using for quantitative. And if you only have the sample statistic stuff, then this is what you need to be using. And in this case, that's what S is up there. It's your sample standard deviation. Oh, it's going to be messed up. It's going to be great. So either today or tomorrow, I am going to be throwing an assessment at you guys in regards to the previous unit. It will be due Friday. Give you plenty of time to get that done. Otherwise, on Wednesday, we are going to be continuing with t-testing and seeing where this kind of takes us. So I got some information to throw at you. Ooh, it's going to be great. If you have not left a comment in the chat, please make sure that you do. That would be fantastic. And I will check that in a little bit. Otherwise, we're going to call it a day there because the bell's going to ring in about 20 seconds. My wife just sent me a picture. Oh, nice. Sorry. It's a long story. I'll tell you later. There's the bell. Bye-bye. Come on. There we go. There's the picture. That's good. Bye-bye, guys. See you. Bye-bye.